control. Do you guys want to learn about robotics? Or no? Okay. If you want, you can stick around, but we're going to talk about robotics. All right. So some logistics. Seated paper discussion 2 will be on Wednesday. I sent an email out to everyone who is presenting and on EdSTEM, so you should know if you're presenting or not. Only 2 groups this time, not 3. And so the presentations will be a bit longer. And homework 3 is due next Thursday. My experience with homework 3 is that it takes a little bit of time to tune the parameters. So like start a little earlier. So there's no like mass panic on Wednesday, you know. Cool. Here's a little quiz. An LQR system has linear cost, quadratic dynamics, quadratic cost, quadratic dynamics, linear dynamics, quadratic cost, none of the above. We covered this a little bit last time. All right, let's keep going. The answer here is linear dynamics quadratic cost. All righty. Let's do a little recap, and then we can get into the weeds of LQR. And so we talked about 3 different types of control schemes so far: bang control, PID control, and pure pursuit. Bang control and PID control were model agnostic. They're super general. They just say try to minimize tracking error by going opposite to the direction of the error. And they're great, but they're not exploiting the model to the max. Pure pursuit is exploiting the model, but it only works for a particular type of model. And so we tried to go from there to something that's more general. That's not just trying to stabilize to a particular point, but rather minimize a cost function, right? And so we went to the idea of optimal control. And the idea behind optimal control is that you want to minimize the sum of costs of a system where the system is evolving according to the dynamics, right? So if your dynamics are F, you're saying that you're going to take actions in the environment U. U is going to help evolve the system X, and then you want to minimize the cumulative sum of costs, right? And so you want to find a set of controls, U1 to T, that minimizes the sum of costs. In reinforcement learning, you maximize the sum of rewards. In control, you minimize the sum of costs, but they're kind of the same thing. Right? So the difference between optimal control and reinforcement learning is just if you know F or not. Right? So optimal control assumes that you know F. You often know the functional form of F. It's a simulator. And you're trying to optimize this objective. Right? So most optimal control problems will look like this. Sometimes you'll have additional constraints. You want to say like U stays within some bounds. You want to say X stays within some bounds. You'll have some additional constraints on your problem. But it's always this type of constrained optimization problem. Okay. A few other assumptions that we note here. We're going to assume that costs are additive, right? Not all systems have to have additive costs, but we'll assume costs are additive. And we'll assume that the system is Markovian in that like the state XT captures everything you need to know about decision making, right? And so sometimes you'll try to optimize for controls. Sometimes you'll try to optimize for a control rule, right? And so the control rule is going to be K, right? And so both of them are kind of within the purview of optimal control. Okay, so this problem has the preferences of your human operator, etc., inside the cost function, and it captures the dynamics of the physics of your system inside of F. And really, all of the methods we're going to discuss are trying to solve this problem, right? Approximately. So the first thing we tried to do was to say, let's consider a really simple type of F and a simple type of C, right? So we said, let's consider F to be linear. Let's consider C to be quadratic. Right? And so this is the LQR system. And we said, this is going to be F, which is linear. This is going to be C, which is quadratic, right? And it's quadratic in state and in action, right? And it's linear in state and in action. So the LQR system is linear dynamics, quadratic cost. And that's going to make it easy to solve that objective that we had last time, right? And so we can say, if you remember, we considered this like inverted pendulum type thing. And this inverted pendulum you can approximate with a linear dynamical system, but not every system can be linear, right? Okay. Any questions about this problem setup? It's just like the Kalman filter, right? But it's just control on this on this problem. And we're going to assume the system is deterministic for now. You can make it stochastic. Okay. So the key idea to solve LQR problems, sorry, let me make sure I'm recording. Okay. The key idea to solve LQR problem is to do dynamic programming. So you're going to go from the back and you're going to keep solving backwards, right? You're going to solve for the optimal control at the last time step, second last time step, the third last time step. You're just going to keep going backwards. And so you're going to use dynamic programming to go from, yeah, sorry. I'm going to use dynamic programming to go from the last time step backwards until you get to the first step, right? And what you're going to try and do in LQR is you're not going to try and come up with a series of controls. Instead, you're going to try and come up with a control law. And we're going to get a linear control law, but you're going to try and say you want to figure out a linear coefficient k such that your control can always be expressed as k times x. Yeah. And so we're going to consider a situation where like you are trying to figure out this control coefficient k, and once you have k, you just execute the controller as kx, right? So if you're in a state x, you get the control as kx and you execute it. So we're going to try and figure out what k is, right? It's not obvious that k is linear yet. We'll solve for why it's linear. But the end result of an LQR process is we're going to like essentially try to solve this problem, but we're going to like force this to be quadratic. We're going to force this to be linear. We're going to solve from the back with dynamic programming. And then we're going to get, what we'll get is we'll get quadratic cost and we'll have linear control. Yeah. Well, I haven't told you how we're going to get there yet, but that's the end result. Okay. So let's start working through this on the back. So we're going to start by solving our LQR problems. Last time I showed you this bunch of nasty, scary looking linear algebra, but we'll unpack it, right? So generally, you're going to define this entity called a cost to go. And so the cost to go is going to say your cost at xt is going to be the minimum of your immediate cost at your current time step plus your best future cost. And so you're going to say that you're saying you're going to assume that you're going to be optimal in the future, right? And it's like being optimal now involves being optimal with the sum of the immediate cost and then the best future cost. And so the reason U is important, U affects two things. U first affects your current immediate cost, and U also affects your next state, right? So if you look at this dynamics, U affects this term, and U also affects this term, because this term is going through the dynamics, right? So U is affecting your current cost, and it's affecting which state you go to in the future, which is going to affect your future cost. And so you can think about your controls as telling you your controls are penalized in the now, but they're also going to affect where you go in the future. And so they're going to be penalized in the future too, indirectly. And so we're going to basically try and solve this problem starting from the back. Okay. Okay. So starting at the last time step, we want to solve this objective, but it's at the last time step, so there's no future cost. It's only present cost. And someone remind me, what's the solution to this thing? What's the solution for U? So two constraints that we remember talking about last time, we said Q and R are positive definite, which means that X transpose QX and U transpose RU are always greater than 0 unless U or X is 0, right? And so with that in mind, what is the minimum of this problem? U is equal to 0, right? And so because these are positive definite, the minimum is U is equal to 0. And if U is equal to 0, then the right term goes to 0, right? So U transpose RU is going to go to 0. which means that the cost at the last time step is X transpose QX. Right? Now, as Marco brought up last time, that cost may not be zero. Right? That cost, like if it depends if your state is zero, your cost is going to be zero. If your state is non-zero, your cost is going to be non-zero, right? And so, but it's the best that you can do. You're at the last time step. That's the best that you can do. Right? And so one way to visualize this is you can think of it as a parabola, a quadratic, around x equal to zero. And so the cost is zero at x equal to zero, and it's quadratic in like a bowl around x equal to zero. Right? Now, like currently we're going to assume that the system is minimized at x equal to zero. If you want to like stabilize your system around a different point, you just have to do a little bit of a change of variable. So you can like do like your cost as x minus x ref and x minus x ref, right? So there your system is trying to be, your cost is going to go to zero when x is equal to x ref. So this one, the one we have right now is zero, but you can like pretty easily change it to a different point. Right? So what is this saying? It's saying in the last time step, the best thing you can do is take no controls. It's like you're fucked already, you know? Just assume, just accept your fate, and u is equal to zero, and you will incur the cost that you will incur because you can't transition anymore. Okay. So just for the sake of our recursion, we're going to call this term P naught, right? And so we're going to say our cost to go J naught at the last time step, this subscript is telling you how many steps you have to go, right? So it's saying that when you have 0 steps to go, your cost is quadratic. It's X transpose QX, which you can write as X transpose P naught X, where P naught is the same as Q, right? These indices will just help us write a recursive equation, right? So that's our cost to go at the last step. Yep. Now, let's go to the second last step. That's the interesting one, right? So we're going to say we're at the second last step. Now your cost will have your second last step and your last step. And so you're going to have your second last step and your optimal cost at your last step, right? And so if you remember, J naught X was X transpose P naught X, but the state you're going to be at is going to be AX plus BU. So at the second last step, let's say you're trying to find the cost at X, you're going to say, what is the immediate cost at X plus the immediate cost on some U? And then you're going to transition because you know the dynamics are linear, right? So you know that xt plus 1 is axt plus but. You know that you're going to transition to a new state ax plus bu, and that's going to be your cost to go for the last step, right? And so you can kind of think of this as your immediate. And you can think of this as your future. Yes. And so we're going to try and minimize this with respect to u. Right, so note that u appears in 2 places. U appears here, u appears here. Okay, and remember that J naught X is defined as X transpose P naught X. Yeah, okay. So we're going to do a little bit of calculus to solve this, but essentially we're just trying to do this minimization with these 2 definitions in mind. Okay, so let's do a little bit of calculus. Help me solve this problem. We want to solve with respect to u. How do I do it? So J1, we're just going to define J naught as X transpose P naught X, right? So first thing we'll do is we'll just substitute, right? So we can write this as min U X transpose QX plus U transpose RU plus AX plus BU transpose P naught AX plus BU, right? All we did is we said that J naught was X transpose P naught X, and we substituted AX plus BU in place of X, right? That makes sense? We had a definition for J naught. We just substituted what J naught is into this equation. And so you can kind of think of this as, this is the cost to go at the state, which is AX plus BU, right? And that is the immediate cost. Immediate cost to go at AX plus BU. Questions? Right, so the only tricky part is like, remember the next state you're going to get to is AX plus BU, and you're going to incur this cost at the state AX plus BU if you acted optimally at the last step. Right? Questions? Got it? Okay. Everyone with me? Okay, good. Um, Sweet. So help me solve this now. What do we do next?
X term goes away.
X term goes away. Beautiful. So you just take the derivative of this equation, right? So you take the derivative. Okay, so Dhruvan told me that this is going to give me 2RU. Also, I don't remember any matrix math, but there's a thing called Matrix Cookbook. You guys should look it up. It's great. It solves all your problems. Or ChatGPT, one of those. But don't bother remembering it. So we have 2RU. And let's have someone else help me with the second term. Can someone else help me take the derivative of the second term? How do we do it? So quadratic, right? I'll come back to you if no one else. You want to crack at it, Violet? No. Okay. Um, Here's maybe one way to approach it, right? Like, try to approach it through the lens of the chain rule, right? And so, like, you have this quadratic term. Just think of it as like do dAx plus bu transpose p naught ax plus bu. Take the gradient with respect to ax plus bu, right? And then do chain rule. So you're going to take dx plus bu with respect to du. Okay. So it's just, you can kind of think of this as just like, if you use change a variable, let's call that thing z for instance, it's going to be dz transpose p naught z by dz, right? Which is like a much less scary term to deal with. Yeah.
Is it just 2p p0 and then times ax plus b?
Yes, exactly. So this term is going to simplify to 2 p naught ax plus bu. And this term is just going to simplify to B transpose. So you're going to end up with 2B transpose P naught AX plus BU, right? So all you need to do is the chain rule. Right? So whenever you have scary terms like this, just do a change of variable and convert it with the chain rule. So what we're going to simplify to, let's see, raise this stuff. Okay, so what we're going to simplify to is you're going to have 2RU plus 2P transpose P naught AX plus BU. Right? Equal to 0. Okay, so now let's simplify it some more. We can like cancel out the 2's, right? So you'll get RU plus B transpose P naught AX plus B transpose P naught BU is equal to 0, right? And so what is U? All we did is we took the gradient, we set it to 0. We're just transposing terms, right? So what is U?
Yes. That's right.
Right. Okay. So let's move this thing over to this side, right? And so we can say R plus B transpose P naught B. This term and this term can be combined, right? Times U is equal to B transpose P naught AX, right? You take the inverse, right? So you can show that U is equal to R plus B transpose P naught B inverse B transpose P naught AX minus. Sorry, good catch. I have a minus missing here. Okay, so here's what we did. We took that term, we substituted what J naught is, which is a quadratic, right? To the gradient with respect to U. First term goes away, second term is a quadratic. Third term is just the chain rule. Right? So use the chain rule. It gives you this thing, This comes from the first part of the chain rule, this comes from the second part of the chain rule. And then we just transpose terms, we moved this side over to this side. And then we multiplied both sides by this thing inverse. Just a little bit of algebra. But it gives us a nice rule, or nice-ish, which is that u is a linear function. Like all of these things are linear, right? So u is a linear function of x. Right? Now everything will become beautiful when we call this whole term k, and so that's the key. Okay, so can I erase this? I have typeset it. Okay, so let's simplify it, right? So we've taken the gradient and set it to 0. Just use the chain rule. We've then done a little bit of transposing, and so you get this objective. We'll unpack it intuitively, right? But like for now, we know that u is this function of x, and we're going to call this thing k. If you remember the Kalman filter, there's also a k term. This is going to be super, super similar to that. You can actually show that LQR and Kalman filtering are duals of each other. They're like exactly the same. One is for filtering, one is for control, but they're very similar. And this term is like almost exactly, it's called the Kalman gain also. It's like almost exactly the same. Right? But that allows us to write u is equal to kx, where k is like this whole thing. Okay? The other thing that you want to do is you want to say this is the optimal u. Now let's compute the optimal cost. Right? So we want to like substitute this thing back into here. Right? It's a little bit of a pain, but we'll try to do it. And the reason that's important is because that'll be important for this third last time step, right? And so what we're going to do is we're going to say that we're going to try and show that the cost to go at the second last time step is also quadratic, but it's a quadratic with not P0, it's with P1, and P1 is like related to P0. And so if you remember what we did at the last time step, we said that the cost to go was x transpose P naught x. At the second last time step, I'm also going to show that the cost to go is a quadratic. It's just that P1 is going to be complicated. But then the same recursion will hold every step after. Okay, so let's try to work out what P1 is going to be. Right? So the way you're going to work out P1 is you're going to take this thingy. Let's call this, let's say u is equal to kx, right? And we're just going to stick it into this guy. Right? So help me work that out. So the first term, so if you look at this thing, it's going to be the cost when you choose the best u is going to be x transpose qx. That term is not affected by u. Plus u transpose ru, where u is equal to kx, which is going to be x transpose k transpose r kx. Right? You can whenever if you have u is equal to kx, then u transpose is equal to x transpose k transpose. Right? And so this is going to say that you take this thing, you substitute it in here, you get x transpose times k transpose rk times x. Right? So you can see that this is like a quadratic with q. This is a quadratic with whatever this thing is, right? And then let's look at the last term, right? And the last term is going to be ax plus bu, but bu is going to be bkx transpose p naught ax plus bkx, right? So you can take x out common from both of these sides, and you can still get something that like looks quadratic. So you can say this is going to be like x transpose of ax plus bk, or ax transpose of a plus bk transpose times p naught of a plus bk times x, right? So it's still a quadratic. It's a quadratic on this complex looking thing, right? So we'll put them all together, but you have to remember how this goes. Just like substitute in u is equal to kx to the first. You'll show that the whole thing is quadratic. First term is already quadratic in x. Second term, if u is linear in x, then the second term is also quadratic in x. And then if u is linear, then the third term is also quadratic. You have a full sum of three quadratics is also quadratic. And so you simplify these things and you can show that it's a quadratic where like your, I don't know what you call these inner terms, like whatever you call it, like the inner quadratic thing is a combination of Q, which is your state cost, KRK, which is your control cost, and this term, which corresponds to your future cost. Right? So you can kind of think of this as intuitively, you can think of this as your current state cost. It's like, how bad is my current state? You can kind of think of this as like my control cost, like how much am I going to incur by taking this control? And then you can kind of think of this as like, if I executed this control and got to a new state, like how much cost am I going to incur from that state in the future, right? So this is current state, current action, future state. Right? And it has all the terms that you know, right? You know A, you know B, you know Q, and K is just this thing, which you also know, right? The nice thing is the same recursion will hold every step, right? And we'll unpack this intuitively. It'll make a little more sense. But kind of think of this as your control is linear in state and your cost is quadratic with a combination of current action, future. Okay. Any questions before we keep going? Okay. So this K term is called your Kalman kink. But we can go from the last step to the second last time to the third last time step. So if you remember what we did to go from the last time step to the second last time step, we basically took this thingy, right? And we said that this thing was going to be quadratic, and we substituted the last term as quadratic. Now to go from the second last time step to the third last time step, you'll do the same thing, but you'll just do it with the J1 of AX plus BU, right? It's just like you're saying that at the third last time step, you're going to get your immediate cost, plus your cost once you have like one less time step available, right? So you can show that like J2 of X is min U of X transpose QX plus U transpose RU plus J1 of AX plus BU, right? Same thing that we did here. The only difference now is that J1, if you remember, J0 was X transpose P naught X, right? That's how we said at the last time step we are going to incur quadratic cost. Now J1 is also quadratic. It's just going to be X transpose P1 X. Right? So like all of the math that you did to go from the last time step to the second last time step will also hold to go from the second last time step to the third last time step. Like you're just going to replace P0 with P1. No changes. Okay, so what that suggests is you can turn this into a recursion where you gain it. If you look at this objective that you get, right, you can access K1 in terms of things like at P0, right? So more generally, you can express Ki in terms of Pi minus 1, right? So it's like when if you can think of it as when you're going backwards, right? The control at this time step is going to be a function of the cost at the previous time step while going from the back, or like one time step ahead if you're going forward, one time step behind if you're going back. Right? So it's like if this is your last time step, right? Let's say like the indices are a little confusing here. So like think of this as like one less time step to go, right? And this is saying that like I here is like number of time steps to go, not number of time steps from the start, number of time steps to go. Right, so you want to go backwards. Think of it as going backwards. So like I will start from 0 and go to T, but 0 means last time step, T means their first time step, right? They're going backwards. That's the part that's a little confusing here. But you can express your K as a function of Pi minus 1 and entities that you know, like P, A, just dynamics of your system, cost and dynamics of your system. And then you can express Pi in terms of K and Pi minus 1, right? So all we're really doing is taking this like equation that we worked out, and we're just like making it a general recursion because it's the same math from time step to time step, right? And so we're just saying that ki is this linear ki is this function of a, b, and pi minus 1, and pi is a function of ki, q, r, a, b, and pi minus 1. Right? And then you can repeat this for pi minus 2. Or you can repeat this for like increasing ki and increasing pi to go all the way back. Right? So you essentially form a recursion. And the nice part about this now is that you can take control, you can like act, right? So you know your optimal controller. If you're in a linear quadratic system, once you compute k, just with some matrix multiply and inversion, you know how to act. Like if you're at x, you take action kix, it's guaranteed to be optimal. It's the best that you can do. And you know that your cost is going to be quadratic, right? And so that's why these are called the Riccati equations, or the discrete algebraic Riccati equations. And so they're discrete diagonally both apart. And so you see that your optimal controller is linear in x, and your optimal cost is quadratic in x. So I think Andy asked this question last time. It's like, why linear and quadratic? Just because it like turns out real nice. And so, and it's like nice because you'll incur like a pretty low runtime. In general, it's not exponential runtime. You'll get like polynomial runtime. You'll have 8 steps of computation because you're going 8 steps backwards, and the n cube and m cube are because you have a matrix multiplied version. And then once you reach the end, you look at some more. Are you like each time step looking ahead and then also taking the first action? So what we're solving is a finite horizon control problem, which means that you're like saying that you have 8 steps to act only. You will not have you don't have infinite time to act. Right. So like if you had infinite time to act, that's like an infinite horizon control problem, and the solution looks a little different. But when you have finite time to act, the solution, if you're at a state with 1 time step to go versus 10 time steps to go, you'll act differently. And so the way this works is that you're going to start from the back and compute all the k's, right? And then when you're executing your controller, you're going to start by executing, like you compute all the k's this way, right? And then you will start by executing k capital H. Then you'll go to the next time step, you'll execute k capital H minus 1. Then you'll go to the next time step, execute k capital H minus 2, all the way till k 0. Right? So like with the pendulum problem, we're saying we only have 10 seconds. That's right. Pendulum so like it's just the solution is a little harder, but you can also work this out in the infinite horizon case. And then so the difference between the finite horizon and the infinite horizon is that in the finite horizon, your controller is time dependent, which means that you play a different strategy at every time. So like the k at time step with 0 steps to go and the k to 10 times to go are different. In the infinite horizon, you play the same strategy every time, right? And so like the thing you're saying with the look ahead, right? Like that's often what you'll do in like an infinite horizon case. In the finite horizon, you play a different controller at every time step. It's kind of like if you're playing a board game and you have like 1 step to go or like 50 steps to go, you'd like play a different strategy, right? So that's the setting here. Good question. Yeah.
What if like the control is bounded by like what you can actually actuate on the robot? Would this like still hold, or is it embedded?
So I mean so you're saying that like in addition to these 2 things, you also have constraints.
Yes, like you can't exert like however much space you want.
So the solution looks different then because your optimization has to satisfy the constraints. And so you'd have to solve a constrained optimization, and that would give you a different solution. So you can apply the constraints to both infinite and finite horizon. But this is an unconstrained optimization problem. That would be a harder problem to solve. Depends on if the constraints are linear or quadratic or what. Okay. Cool. Right. So given this, right, you can kind of construct an algorithm that looks like this. The algorithm goes backwards in time, right? So if you're at the base case, your control k is 0, right? And your quadratic term is q, right? That's what p0 was. That's the base case. That's the last time step. And otherwise, you go backwards in time, where you say you get pi minus 1 from the previous step. You compute ki for pi minus 1, and you compute pi from ki and all the other terms, right? And so what you would do is you'd run this thing backwards in time. From the last time step to the first time step, compute all the ki's, and then you would play the controllers forward, right? And so it's kind of like, you know how backpropagation works, it's like you have a forward pass and a backward pass, right? And so here, similarly, you compute all the k's going back, and then you would play the k's going forward. And so what that means is that you'd start from, the indices are the thing that's confusing here, right? So let's say you start from the last, oh, yikes. Let's say you start from the last step, right? So you start from, my iPad is being finicky. Okay, so if you start from the last time step, you would compute K0, you'd compute K1, K2, all the way till KH, right? And so this is, the subscript is telling you how many steps you have to go, right? And so then you compute all of these, and now you have to run your system, right? You have to run your robot in the world. And so when you run your robot, you first run KH, like let's say you're at state X, you run U is equal to KHX, you get to some new state, X prime, then you run U is equal to KH minus 1, X prime. You get to a new state, let's call it X prime prime, then you will run U is equal to KH minus 2, X prime prime, and so on, right? So you compute the controllers backwards and then you run them forwards. Yes? So that's the basic idea of LQR. Let's kind of try to put some intuition on it, because these matrix multiplies are a bit intimidating, right? And so what I'm going to assert is it's kind of like Kalman filtering. Do you guys remember the Kalman gain in Kalman filtering, this like nasty looking K term in the observation step? So from Kalman filtering, we had this sigma C transpose sigma C plus R. Like if you remember how we call this thing K, and then we had, Jesus, sorry. We call this thing K, right? And then what we had is we had our mean was adjusted by like mu plus K times Y naught minus C mu or something. And then our variance was shrunk by I minus KC times sigma. If you remember, like our Kalman filtering equation, it kind of looks, the observation step looks something like this, right? And the intuition we put behind the K in Kalman filtering was that it helps you trade off between how much you should trust your sensor versus how much you should trust your current variance, right? So you can kind of think of it as a ratio between sigma and R, right? So we said that if R is super high, which means your sensor is like completely noisy, don't trust it at all. And if R is 0, which means that your sensor is completely accurate, trust it completely, right? And so it kind of like lets you trade off between those things. Now, the K term in Kalman in LQR is pretty similar. Right? So if you look at the K term in LQR, it's B transpose Pi minus 1 A and R plus B transpose Pi minus 1 B. Let's set A and B to identity, just to make everything simple, right? You can think of A and B as translating between different spaces. Let's just set them to identity. If you set them to identity, you get the like K term is basically Pi minus 1 divided by R plus Pi minus 1. Right, so what it's telling you is, you can kind of think of this as Pi minus 1 is telling you the cost in the future, and R is telling you your immediate cost, right? And so in some ways, what this thing is doing is it's helping you trade off between Pi minus 1 and R. Right, so if Pi minus 1 is going to dominate this, it's going to be super high compared to R. You're really going to pay attention to the future. You don't care about the present. And if Pi minus 1 is going to be small compared to R, you're going to be greedy and optimize for the present. You don't really care about the future, right? And so you can kind of think of this like A term, just like in Kalman filtering, it traded off between your current sensor and your variance, right? You can think of it as trading off between your current cost and your future cost. So it's like basically the same calculus. You're trading off between the R. Earlier, you were trading off between sigma and R. Here, you're trading off between Pi minus 1 and R. And in this case, it was like sensor noise versus variance. In this case, it's current cost versus future cost. Right? And so that's kind of, at least that's how I like to think about this intuitively. And so like, it's always a tension between how much you optimize now versus how much you optimize in the future. So in some ways, you can think of the quadratic term as a mix of your current state cost, your current action cost, and then your optimal cost in the future, right? And so the K lets you trade off how much you care about the future versus. Okay, so that's LQR. So the nice part about LQR is you can write down a really efficient equation. If your system is linear and quadratic, you don't have to solve some really complicated thing, no GPUs, no nothing, just a matrix multiply. And if your system is linear and quadratic, you should just apply this Riccati equation. It's optimal. Right? Lots of extensions, which I was actually hoping to cover, but we might have to do next time. But here's some examples. So this is from Peter Beal back in the early 2000s, but he was flying things like flying a helicopter upside down in Stanford with LQR. It's a small variant of LQR, but it's definitely pretty out there. When I was a PhD student, we actually had the helicopter that was running this in our lab, so it's pretty awesome. But the cool thing about this is that it's not a linear system. What they did is they approximated a nonlinear system with like a series of linear systems, and were able to do like pretty cool maneuvers back in the olden days. You can also apply this on like locomotion systems or navigation systems, and it's a pretty versatile thing. There's ways to make it work for nonlinear systems that we'll cover, but yeah, generally it tends to work quite well. That's very simple. Good, Mark. It's not. It's what they do is we'll see if we can talk about it now, but it's you take a nonlinear system and you approximate it with a Taylor approximation as a linear system. Okay, so that is LQR. Yes. Yeah, they're doing path tracking. Yeah. Correct. So the way that those, for instance, the Stanford example was set up was it's trying to do path tracking. So like Peter set up like a reference path, and then it's trying to stabilize your out there reference path. The most control is like stabilization. So like a lot of RL is about like finding the right path and so on. In control, you'll often assume that you know the right path coming from planning or something. You're stabilizing around that path. Good question. Okay, so as we've talked about, this is a linear system with quadratic cost, which is not most systems in the world, right? And so to go from here to things that are useful, we have to go to things that are stochastic, things that are nonlinear, things that are time varying. Like you're talking about just like things that do trajectory following. Someone have a question or just stretching? Okay, no, no problem. So let's see if we can get through a few of these, but these kinds of things make LQR more practical. Okay? So let's start by just thinking about nonlinear systems. And so in a nonlinear system, you're saying that your dynamics are not linear. There's some nonlinear function f, right? And for now, let's say you're trying to do stabilization around a point, which means that like you want to keep your system at some state x star. And there exists some u star such that the system is stable at x star, right? Which means that if I was at x star and I applied some action u star, the system would continue to remain at x star. So it's a fixed point of your system, right? When I say it's a fixed point, I mean that if I was at x star, I applied u star, it continues to remain x star, it remains at rest. So in this kind of situation, what we're going to do is we're going to approximate this nonlinear system with a linear system. And so we're going to say, let's linearize the dynamics. When you say linearize, that means take a first order Taylor approximation around x star. So you're going to linearize your dynamics around x star and u star. And so it's a multivariate function. And so the Taylor approximation will have a gradient with respect to x and a gradient with respect to u. Right? So if you remember how the Taylor approximation worked, you can say that f of x is f of a plus f prime a x minus a plus f double prime a x minus a the whole square, so on, right? So we're just going to take the first order Taylor approximation, but multivariate, right? So what you're going to have is you're going to linearize it around x star and u star, which means that this function f is going to be approximated as f of x star u star plus the partial derivative with respect to x times x minus x star plus the partial derivative with respect to u of u minus u star. Right? So this is what your Taylor approximation is going to be. Now, the nice thing about this is that, so you can kind of, like, these are a little hard to visualize, but these are essentially matrices. Right? So like, let's say your x was of dimension m by 1 and your u was of dimension n by 1. This is going to be a matrix of dimension m by m. It's called your Jacobian. It's going to be basically your output is going to be m dimensional. Your derivative with respect to something that is m dimensional, so it's going to be m by m. So it's like basically f takes in an m by 1 thing, an n by 1 thing, and gives me an m by 1 thing. And so if I'm going to take the gradient of this thing with respect to x, it is going to be an m by m matrix. Similarly, this thing is going to take in x and u and give me something that is m by 1. And I want to take the gradient of this thing with respect to u, which is n by 1, which means that this whole thing is a matrix of m by n. Right? So these are the Jacobians, but you can kind of start to see starts to look like a linear system again, right? So you can see that like we can rewrite our system as xt plus 1 minus x star. We linearized around x star, which we know is the fixed point. So you can write the system as xt plus 1 minus x star is equal to a, approximately equal to a times xt minus x star plus b times ut minus u star. Right? So you can say that like this is basically the partial derivative here. This is the partial derivative here. Right? That's what your a and b is. And so all we did is we took the Taylor approximation of our f around x star and u star. And so now what you'll do is you'll like do a simple change of variables. So you'll say, let's call zt equal to xt minus x star. Let's call vt equal to ut minus u star. And then you directly get a linear system. Right? And so now you directly have a linear system that came from this nonlinear system. So we took a nonlinear system, we just applied the Taylor, the Taylor expansion, the first order Taylor expansion, but multivariate. We did a little bit of change of variables, and now you've converted into a linear system. Once you have a linear system, just apply all the LQR magic, right? And so that's kind of what Peter did in like his helicopter example. Like he just basically took a nonlinear system and applied the Taylor approximation. You have to keep reapproximating it, but it like gives you a way to use all the LQR machinery by like sticking all the nonlinearity into these matrices. Okay. I think we are out of time, but we'll talk about MPC next time. Right? Thanks.